So this is where we'll be focusing on the unit commitment issue. In the last class, we went through this slide, but let me go through this again a little bit. So the main driving force for thinking about the unit commitment issue is basically the variation or the varying nature of the load throughout a day or a week or a month or whatever time span you take. So what we did basically in the last topic of this course, what we did is basically, let's say we fixed our concentration on any of these demands, okay, on any of these demands. Let's say we thought that, okay, let's say if our average demand on our power generating units is, let's say 0.4 kilowatt, according to this diagram, 0.4 kilowatt, then how are we going to generate, or how are we going to have generation out of my generations in an optimum way to satisfy this demand with some constraints in mind? Okay, so that was economic load dispatch. So in the economic load dispatch, you can simply say we fix our time at a certain instant. Okay, we set our time at a certain instant, let's say at the first hour or the second hour or any 10th hour of the day or of the whatever time span you take, month or year. And then from the available generating units, from the available or online generating units, how are you going to play with those to satisfy that demand? Okay, so in the economic load dispatch, we are basically focusing on a very small time span or a unique time span, you can say, for a unique demand, not varying demand. That is economic load dispatch. So in the economic load dispatch, you have a unique load demand value. First point. Second point is, you know beforehand what or which units are available to you for generation, which units are already available to you. So these are these 2 points are specifically related with the economic load dispatch issue. But the problem is that if I look at the bigger picture or the larger picture, I will have to think about these variation, okay, throughout the day, throughout the hour, in the weekends or in the weekdays, or even on a year basis or a seasonal basis. My peak values will change, the valleys and the peaks of the load curves will change continuously. Okay, so I cannot fix my concentration on any single load. Rather, I have to think about a bigger picture. Okay, because my power stations are installed to satisfy the demands throughout a year or throughout, I mean, whatever demand is there, okay, not for a single instant. So to satisfy this load demand, what we said in the last class is that because the load is varying, so the main thing is behind these unit commitment issues. That means we have to also keep the source varying. Okay, output, we have to also keep the output varying, and we also have to choose the available units in some intelligent manner, not arbitrarily. Okay, not arbitrary. The choice of units which are available should be chosen by some intelligent manner. So that manner or that choice will be provided by the unit commitment solution. Okay, which units we are going to use or which units we are going to make available at a certain time instant to satisfy a certain load demand. That is unit commitment. Okay, so let's go into little detail on this. Okay, so yeah.
Please, can you come back again? I didn't get it.
I can't hear you. Yeah, yeah, walaikum assalam. Yes, walaikum assalam.
I said, sir, I didn't get it. Please, can you repeat it, sir?
No problem. I will keep this repeating throughout the lecture, so don't worry. What I said, let me summarize. I said in the unit commitment issue, okay, let me talk about the economic load dispatch. In the economic load dispatch, what we said that we have we have a known value of demand, right? Let's say 500 megawatt or 900 megawatt, whatever. We have a known value of demand, okay? And we also had the information that we always kept on saying that we have some available units. We know that we have 3 units, or we know we have 2 units, or how many units we have. We already knew it before we started solving the economic load dispatch. We already knew it, what is the demand, okay? So the demand was a fixed value there in the economic load dispatch, and the units which are available for that, for satisfying that demand, that information was also available. Those things are related with the economic load dispatch. In the unit commitment, what we will deal with, basically, we will try to satisfy the demands in a varying manner. You see, it is varying. The load is not fixed at a certain megawatt or kilowatt. It is continuously varying, okay? So accordingly, we have to turn on or turn off certain generators. We have to make them available for a certain duration. Let's say the load is low here, okay? During this hour, the load is very low, the lowest around this duration. So if I have, let's say I have bought 5 generators to satisfy this demand here. So when the demand is here, lying here, I don't have to run all the 5 generators. I don't have to make the 5 generators available at the same time. So I have to choose which generators should be made available to satisfy this demand, or this demand, or this demand, or this demand, and so on. So that topic will be taken, or that problem or that solution will be provided from the study of unit commitment issue, okay? Dodo?
Yes, sir. Yes, sir.
Okay. Do you get it?
Yes, I get it.
Okay.
I have an idea.
Okay. So this is what we have already said, but let me go through this. So the first question is it a problem in the operation of electric power system? Of course, it is a problem, because we can't keep all the units running all the time for a varying demand, okay? We can't keep them running all the time. So all the units should not be kept on all the time, because it is associated with economics. If I don't need it, if I don't need it to run to satisfy the demand, then I can keep it turned off. So the next thing, why don't we simply commit enough units? Okay, that is to say, if I know the second point here, I'm focusing on this point here, okay, the second point. So it is saying, what is the problem if I know that my maximum demand can reach up to, let's say, 1 kilowatt in weekdays. Okay, overall in a week, my demand can reach up to 1 kilowatt. So why not keep sufficient generating units on for the whole week and leave them as on, which can satisfy this 0.3 kilowatt as well as 1 kilowatt, okay? Because the units which can satisfy this 1 kilowatt, automatically they should be able to satisfy this low demand, right? So what is the issue? What is the problem? The problem is that of economics. You don't want to spoil your money, okay, where it is not necessary, because you don't need to run all the units to satisfy 0.3 kilowatt demand. 0.3 kilowatt is a very low demand. So if it is possible to satisfy this demand with only 1 unit on, then you will go with that. You don't have to run all the 5 units or all the 3 units that you have, okay? So here is a little explanation of what is meant by the commitment or the term commit. By the term commit here, we mean we have to turn on a unit. By a unit, it has to be clear, it is not only the generating unit, because we are talking about the thermal units. So what else do you expect? You expect to have a boiler unit, you expect to have a turbine unit, you expect to have the generating unit, you also expect to have some auxiliary units, okay, associated with the proper operation of these 3. So you have to turn on all those things. You have to bring your rotor or the turbine, the prime mover, to speed. To speed means, let's say we are talking about synchronous machine. So you have to bring it to the synchronous speed. Then you have to synchronize it to the system, which is running at a certain frequency and providing a certain output voltage. So you have to synchronize it to your already running system, okay? And finally, you have to connect it to the network, and share some load. So this is what is meant by commitment. Okay. Okay. So then, as I mentioned already, that we can't keep enough units on forever. We can't do this because it is associated with the economics, the money.
So
Yeah.
yeah, since we know that starting a unit is taking a longer time, so can we anticipate that, for example, if you know that at that time of the day there will be a demand, but
Yeah.
to start the unit, then the need will be already passed. For example, the customer will not be available when the unit will be available. So how to do that?
I got your question exactly completely. Can you give some values here? What you are talking about? I have opened this slide here
Okay,
for you.
for example, if we can see the maximum here,
Yeah, the maximum is, let's say, 1 kilowatt around. Yeah.
okay, let's say now that this demand is needed, for example, at 12 o'clock,
Yeah.
okay, but at 8 o'clock we have 3 units for need. So to satisfy this demand, maybe we need 4 to 5 units. But for the fourth and fifth unit to start, it will take very much long time. So should we anticipate that, or we have to wait until that time when the
No, no,
demand
no,
is
no.
needed, then
All
we
these,
start running the unit?
yeah, yeah, excellent question. Yeah, we can't switch on and switch off arbitrarily. Okay, there are certain constraints. The topic you are mentioning, these are known as minimum uptime or downtime. We will take it later on. Okay, we'll take this issue later on when we talk about the constraints for unit commitment. Okay, so till then, I think you better wait. Okay, so you cannot arbitrarily turn on and turn off whenever, wherever you want. So you have to satisfy some constraints. Okay. Like like, let's say some units are turned on at hour number 10 of the day. You can't instantly turn on, let's say, the remaining units arbitrarily, although they are giving you the most economic solution, probably because they have some constraints. They cannot be turned on immediately or before a certain time duration. Similarly, they cannot be turned off. Some units cannot be turned off from here to here. You have to turn off some units, okay, because the load is decreasing. So you like to reduce some generation by turning them off, but you cannot do this arbitrarily, okay? So that thing will be taken in the constraint part. We will discuss that. Sure. Thank you. Okay, so now, as we said, it's quite expensive to run run too many generating units unnecessarily. Okay? You don't need it if you're not constrained, so you don't run them. It is quite expensive. Okay, so you can save a great deal of money if you turn them off, if not needed. Okay? By decommitment, we mean you just turn the units off. Okay, you just turn the units off. So that means you have to go back in the reverse direction of commitment. So the commitment goes from you turn the unit on, you bring them to speed, you synchronize them, you connect them to the network. Decommitment goes in the reverse direction. Simple. So now let's give you a small example with a picture about what's the difference between ELD, economic load dispatch, and unit commitment. So now I think it would be a little more clearer if I go through the pictures. On the left diagram here, ELD, you show this is the ELD. So in the ELD, we have some information about the load. Okay, we know what's the load, and the load is fixed at a certain value. And we know that, let's say, out of many generating units, okay, let's say there could be many other units. We know which units are now available. Okay. That is to say, it is certainly known that generator 1, 2, and 3, all these are available now when the load L1 has a certain value at a certain instant. So then the ELD gives me the solution that what would be their optimal combination. Okay, you have to use up both all these three, G1, G2, and G3 in the most optimum manner. That is ELD. Whereas the unit commitment, you actually don't know. Okay, you are actually looking for the answer that which units you should make available to satisfy a certain demand. Okay, to satisfy a certain demand, which could be varying over a period of time. Okay, which would be varying over a period of time. So keeping the L1 variable, the unit commitment looks for the answer that which of the units among these three, let's say, could be turned on or turned off, or should be turned on and turned off. Okay, in the current picture, you have G2 only running. Okay, only G2 is running online. It is committed. G1 and G3 are decommitted. They are off. They are not online. Okay, they are not synchronized. They are not connected to the network. So when the load increases here, then what you do? Either you increase if there is any available generation from G2, you increase it, or you look for some other combination. Either you turn on G1 or you turn on G3 and so on. If you have reduced load, then probably you reduce the generation from G2 itself, or you take any other combination. That answer will be obtained from unit commitment. Okay? Any question on this diagram?
So which one will be the best one?
Which one will be the best one? Among whom or between whom?
Among ELD and UC.
Okay. Basically, ELD is a sub portion of UC. The next slide mentions about that. And when we solve the problem, you will see that ELD is just a subsection of unit commitment. ELD is a subsection of the total unit commitment problem statement. What is meant here, if you know, okay, the G2 is available, okay, let's say you know now G1 and G2 should be made available. That decision will come from unit commitment. Now, once G1 and G2 becomes available, then the problem goes to ELD. ELD gives you the answer. What should be their combination between G1 and G2? Do you get my point? I mean, they are not competitor. This ELD is simply a part of unit commitment. First, you have to decide about unit commitment. You have to know which units are available. Once you know which units are available, you just play with them. Which should be bearing how much load, which should be providing how much generation. They are not competitors. They are not two ways to look into the same problem. Unit commitment gives you the idea which unit should be turned on and which unit should be turned off. Unit commitment, I mean the top level decision of unit commitment don't give you the solution of what should be the economic what should be the economic combination, what should be the optimal combination between them. Whereas ELD gives you the internal decision, the low level decision or inner decision, that what should be the contribution from them. Okay, we'll take the example, and as we go on, probably all these queries will be inshallah answered. So here it is mentioned, your query is actually answered here in this slide. So more difficult to solve than ELD. Of course, it is a top level problem. Or in the hierarchy of decision making, it is a top level decision making process. And then once you know which units are available, then you apply ELD. ELD is a part of unit commitment. It is not something new. It is not something other than unit commitment. It is a part of unit commitment. So unit commitment gives you the bigger picture. ELD gives you the inner picture. Internally, how you are going to solve, how you are going to share the loads among the generations. Okay. The problem is a little more complex in unit commitment due to these things. You see, in the ELD case, okay, in the ELD case here, you know you have a certain demand, and let's say you know their capacity, G1, G2, and G3, all their capacities are known. So what you have to do, you have to look for some solution variables here, and you can look through some continuous domain. What I meant by continuous domain, even in the decimal points you can go. Okay, like if let's say the load is 450 here, so you can choose like, should it be 100, 100 and 250, or 99 point something, and the remaining shared among them, like this. So you can choose your solution vectors from continuous domain. Whereas unit commitment, the on off status, is it a continuous solution vector? Either or on or off. It is an integer variable. Okay, it is an integer decision variable. So if the unit is on, you say it is 1. If the unit is off, you say it is 0. So you have to choose between only two solutions, either 1 or 0, but you can't choose 0.5 here. This is what I mean. I mean, you can't say my unit is half on and half off, or 70% on, 30% off. So you can't go for any continuous solution. Either you have to take decision 1 or 0. So unit should be on or off. So this kind of programming problem is known as integer programming. Okay, integer programming, where you have to decide on whether you choose on or off. On off situation is one example of integer decision variable. Okay, you can't choose any in between, any values in between. You can't choose 0.7 for unit commitment problem decision making. On or off, you have to choose 1 or 0. So this is integer, and as we said, ELD is a sub problem of the unit commitment. So in total or overall, the whole thing, we call it mixed integer programming. Okay, mixed integer programming. Mixed integer means this: you have some decision variables in terms of integer variable, like unit, whether the unit should be on or off. So that is integer type decision variable. And some continuous variable is what? Unit output. Should it be 99 megawatt or 100 megawatt or 99.99 megawatt or whatever. So that is continuous type decision. Okay. But this unit on off, commitment, decommitment, this is integer type variable. So the programming problem where you have to choose, or the optimization problem where you have to choose both decisions in a single problem, those are known as mixed integer programming. Okay, where you have some variables in continuous form, in continuous domain, and some variables in integer domain. So we call it mixed integer programming. Okay. Okay, now slowly let's go into, we have talked a lot about the theoretical part. Let's slowly try to solve some examples and make our concepts more clear. So here is one example. We have, let's say we have bought 3 units. Okay, we are not saying anymore that these 3 units are available now. We are saying we have 3 units and these are their data. So the units have their minimum generation capacity in the leftmost column. The first column here, it gives us 150 megawatt, 100 megawatt and 50 megawatt. So let's say this is unit number 1, this is unit number 2, and this is unit number 3. So all the units have their minimum capacity and maximum capacity in the first 2 columns. They have their heat rate. Remember, we talked about the heat rate curve. The unit is given in MBTU per hour. So heat rate is a function of the generation of an individual unit. Okay, so you see this PG1, heat rate is a function of unit 1 generation. The heat rate for unit 2 here is a function of unit 2 generation, and so on. The fuel cost is given in dollars per millions of BTU, and let's say the demand is 550. Okay. Now the question is how you should choose, or what units should be used to supply the load most economically. Okay. So now there is one solution given. One way, one simple way, or simplest way, we should say, to try out all the possible combinations. Try out all the possible combinations among these 3 units. So how many total combinations will be there if I try out all their combinations from among 3 units?
9.
2 to the power 3. Okay. Just go through the DLD topic. simply the first three columns here. You just read out 0, 0, 0, 0, 0, 1, 0, 1, 0, and up to 1, 1, 1. So there will be 8 combinations, okay? 2 to the power 3. So 8 combinations. Okay. So simply we have listed them as in the DLD fashion because our decision is now 0 or 1, right? We have to decide between 0 or 1. For the first level decision making in the unit commitment, we have to first decide which units should be turned on and which units should be turned off, kept turned off. So we take all their possible combinations. We get these 8 combinations for the 3 units. That's done. No explanation is required here, I think. So you can either read them as 0, 0, 0, and here it is 1, 1, 1. So all the units are on here and all the units are off here, okay, the topmost one. Then we just calculate the summation of the maximum capacity. So because the topmost one we have none of the units available. So the sum actually 0 and 0. This is called as infeasible because it is not able to satisfy your demand. Okay, so this is not a feasible solution. Anyway, we go for the next one. So we turn unit number 3 on and see what is the maximum. So you simply choose the maximum for unit number 3 here because only one unit is on among the 3, which is the third unit. So third unit maximum is taken here, 200 in this column, and only the minimum of the third unit is taken here, which is 50. Okay, so which is 50 I've listed here. And similarly here, so if you have unit 2 on, you simply take the maximum of unit 2, minimum of unit 2. If 2 of them are on, then you just sum them, add them up, add the maximum of unit 2 and 3. So how much is it? So this is unit 2, this is unit 3. So maximum summation would be 600 and minimum summation would be 150. So this is 600 and 150. Okay. In this way, we complete these 2 lines, these 2 columns. Okay. So interestingly, the next 2 here, if you look at the rightmost column here, the second choice and the third choice, or the second combination and the third combination, both of them yield infeasible solutions. Why? Because even their maximum capacity, additive maximum capacity or individual, the maximum capacity out of this combination and out of the second combination and the third combination are still not sufficient to satisfy your demand of 550 megawatt. Okay, this is why these 2, that means starting from 1, 2, and 3, the first 3 are infeasible because their generation capacity is not enough to meet the demand. Clear why they are infeasible? Okay. From next on, from the 4th combination up to the 8th combination, you see the maximum is increasing slowly. Okay? Because clearly we are having more generation here, more units being turned on, and ultimately we have the total combination here 1200. If we turn all the units on simultaneously, that means if we make them available simultaneously, so the maximum is 1200, the minimum is 300. Now up to this column is clear. So these 3 along with these 2, this gives us some sort of the initial flavor of unit commitment problem. The next 3 columns here, P1, P2, P3, this decision will be obtained from ELD. So thus ELD is a sub part of unit commitment. Is it clear now? That is to say, how we are going to divide that 550 megawatt load demand, among the available units. So what is the available unit here? In this 4th row, you have the combination, 4th combination, you have both unit 2 and unit 3 on, right? So this is given from unit commitment. Okay, or this is, we are taking some combinations that we will keep it on and we will keep it on. But how the load will be divided? This 150 decision, this decision of 400 and this decision of 150. That is, I will take 400 out of generator number 2 and I will take 150 from generator number 3. This decision will be obtained from the solution of ELD. Okay. Thus, ELD is a sub part of unit commitment problem. Is that clear now? So they are actually
Yes, sir.
not competitor. This is a sub part. ELD is basically a sub part of unit commitment problem. So now how do you calculate the cost? Because your unit 1 here is off, P1 is 0, because your first unit was off here in the fourth combination. So F1 would be 0, because you are not running your unit 1, but you are running unit 2 and unit 3. So you can simply calculate your cost using this information here. Okay, this information here. So that is calculated. You've got 3760 and you've got 1658. So this is your total cost FT, and accordingly you complete all the remaining all the remaining combinations here, starting from 5, 6, 7, and 8. You calculate, you obtain these values P1, P2, and P3. These three values are obtained from the ELD solution, and accordingly you calculate the cost, individual cost, F1, F2, and F3, and then finally you can calculate FT. So starting from combination number 4 up to combination number 8, all are feasible solutions. Which one is the optimum? The one which gives you the least cost. Okay, this is highlighted in red color. So if I just go through by naked eye, we can simply check them, and we find that 5389 is the minimum cost. So that means if I run unit 1 alone, I can satisfy the demand in the most economic way. Okay, clear?
Yes, sir.
Any question on this table? I hope no question. And I think now the whatever confusion was there between ELD and UC, after this table, I think that is clear now. That is over. The confusion should be over now. But the thing is that in this example, actually, we have not imposed any constraints. I mean, not any equality constraint or any other kind of constraint. Our only one constraint was we have to satisfy the demand in some way. Okay, so we can say we only considered the equality constraint, that summation of P generation should be equal to the demand. Okay, only that constraint was taken. Any other constraint associated with the unit commitment problem, specific constraints we will discuss later on. So those constraints are not yet taken. This is just a very simple example of decision making using unit commitment problem, but there are much more complex things waiting. Okay, so this is what we have seen till now about the turning on of units. Okay, if you have a unit, how you can keep them turn on and keep one of them on, or keep more than one on and satisfy the demand in the most economic way. Now, in this case, in this example, we considered we have only a single load demand. Okay, the load is not varying. So we can say we took the example of a single load at a certain instant of a day. What would happen if my load is varying in this way? Okay, let's say the load starting from 4 p.m. of a day, my load was, let's say, started from very high value, 1200 megawatt, and it was kept there, let's say, up to 6 o'clock, 6 p.m., and then from 6 to 7 or whatever time, I mean, I don't know the span, 4, so maybe this is, yeah, 6 hours. Yeah, so this is 6 hours break. So 4, 8, 4, 8, and 4. Okay, so this is 6 hours break. So for the first 6 hours, it remains at 1200, then it gradually decreases. At 4 a.m. in the morning, it remains at 500 megawatt, and then it rises slowly as the day goes on. So this is the 24-hour period load profile. So now we are looking at another example. Now we are thinking about unit decommitment, okay? Not the commitment, but decommitment, and how we are going to turn off our units. Because now we have the same units. Okay, you see we are choosing the same units as we chose here, 150, 600, all the heat rates, all the fuel costs, everything is same. Fuel costs are same. Only thing is changing here is the varying nature of the demand. Previously it was fixed at 550 megawatt, now it is varying. So the question is which units to decommit and when. Okay, which units we are going to turn off and when. So again, we are taking some very simple strategy here, very simple shutdown rule. We can say now, because our load is actually, we can say in the first half cycle, in the first half, in this first half from 4 p.m. to 4 a.m., the load is actually decreasing. So we took that as an example. We basically, again, we went for all the possible combinations because the load started from a pretty high value. So we also started from the status or from the combination where all the units were turned on or made available, okay, because the load was high. And slowly or gradually we reduced the units which are turned on, and finally we kept probably only one unit at the end where we have the minimum value reached, 500 megawatt. So what is the rule being followed here? The rule being followed here is basically by observation. Okay, there is no magic. This is simply observation. This is not some algorithm, some critical or complex algorithms. This is simply some by observation. What we see is that our load is varying between 500 and 1200. Okay, this is observation number one. So 500 is the low value, lowest value. 1200 is the highest value, the peak value. And we observe that the summation of all the three units, maximum summation can give me here, you see 600, 400 and 200. If I add them, I will get 1200. So that means to satisfy this, I of course have to turn on all the units at a time. Okay, is that clear? This sums up to 1200, so I have to turn them on. Then I simply follow a strategy here which is listed here. So when the load is above 1000, run all three units. So when the load is above 1000 means what? So you have 600 and 400. This can give you 1000. This is how the 1000 value is coming. So if the value is beyond 1000, that means you have to take all these three, right? So 1000 is a slab. You can say one step. So beyond 1000, we have to turn all them on. If your load is less than 1000, okay, just below 1000, then you can choose these two. So you have to, or you can turn this off. So you can see when the load is 1200, so it is on, up to 1050, we have turned all of them on. Once it goes lower than 1000, we simply turn unit 3 off. Okay. Next, how we choose the next value, that is this between 1000 and 600. This is the next slab or next decision. Why we choose 600? Because again, if we look at this data, 600 means what? 600, you can either choose this one or either you can choose this one. Okay, for this example, they actually, if you sum them up, you get the same value. If you individually run this, you can get same value. So that's how 1000 is the combination of these two highest two generators. 600 is the individual contribution from the highest capacity generator. So this is how 1000 is the summation of these two. 600 is the individual maximum of available these three. So this is how we choose 1000 and 600. I'm again saying this is simply observation. There is no algorithm, simply observation. That's why it is called simple shutdown rule. Okay, so once it reaches beyond 600, that means, okay, below 600. So up to 650, okay, up to 650, we keep these two on. Okay, so between 1000 and 600, you see these two are on. So from 950 to 650, okay, these two are on. Once it goes to 600 or lower, we simply turn unit 1 on and we keep others off. So this is a simple shutdown rule, okay, for decommitment. And there is no magic. There is no algorithm. It's simply by observation. Okay, now we will slowly go into the constraints associated with the unit commitment. Okay, the first one is spinning reserve. The first constraint
Uh,
unit,
so
yeah,
can you please go back to the previous slide?
this one.
Yes, sir.
Okay.
I would like to say it would not be best if we can turn off unit 2 at 550, because normally if the output is 600, that means you will not get exactly 600. You may get more than that.
Unfortunately, unit 2 can only provide 400. That's why. Okay. Your 400 is not sufficient to supply 550. Do you get my point?
Yes.
Isaac,
Yes, sir.
you get my point?
Yes, sir.
If you had 550 here, let's say, then you have to choose probably by some economic dispatch algorithm. But here the values are actually chosen in such a way that makes your life easy. Okay, just for simple explanation of the rule. Or in that case, you would have summed up these two. Okay, so in those case, it would be 1150, 600 plus 550. So it would be 1150, something like that, instead of 1000. Okay, the numericals value, the slabs would be changed here. Instead of 1000, it would have been 1150. It would have been 1150, and this 600 would have been 550 plus 200, 750. Do you get my point?
Yes, sir.
So
Yeah.
accordingly, these values would have been changed. Okay.
Yes, sir.
Okay. Thank you.
Yes, sir.
Yeah. Any question?
Yeah.
Yeah.
I have also a question maybe related to that. We know that with time the units will not be able to reach their maximum that we are using now. For example, they will be degraded, they cannot reach the 600. So these assumptions will not work at that time again.
Yeah. About 600. What do you say?
For example, with time, we know that the units will not be able to reach the same maximum that they are reaching now.
It's difficult. If I,
Yeah, for example, on the previous slide,
yeah, on the previous slide, yeah.
we can see that the unit 1 is having the maximum of 600.
Yeah, unit
So,
1
for
max.
example, after some years of working, you know that
Yeah,
we
yeah,
will
you
be
are
able
all,
to reach
you are
600.
whatever you're talking, all are part of constraints. Till now, I say we have not considered any constraint associated with the unit commitment problem. These are, in terms of unit commitment constraints, these are, you can say, unconstrained problem. Okay. So you are saying probably, okay, if the machines are aged, they are old, so their efficiency will be reduced. They would not be able to provide you 600, although their rating is 600, right?
Yes, sir.
So then their derated capacity will be used. Instead of 600, you have to consider, let's say if it is 580, you have to write it down 580 while you solve this problem. You get my point?
Okay.
I mean, you would not take 600 here. You have to take 580 there. Okay? The derated capacity. Thank you. Okay. So now let's slowly go into the constraints of unit commitments. Number one constraint is a spinning reserve. What is spinning reserve? Anyone? Probably you have heard this term before. The formula is given here, but can you recall? Or have you studied this before? Okay, what is reserve? Forget about spinning. What is reserve?
So it's the amount of power that we're producing in excess of.
In excess, yeah. So whenever we need it urgently, you can call it up. Okay, you can call up on that, and they will serve it. Okay, in emergency case. So this is reserve. Spinning reserve means, because we are talking about some rotating machineries, so spinning reserve means specifically I am talking about this thing, the generation available from all the rotating units, we should say, or all the synchronized units. Okay, because once the unit is synchronized, you need minimum time to get the output available. Okay, whenever you need, you can simply bring it. You simply You connect the machine, you connect the generator to your network. On the other hand, if your generation is not synchronized beforehand, because synchronization would require some time, right? Synchronization, that means you turn your system. You remember what is the definition of unit commitment or unit commit? The term by the term commit, we mean you have to turn on the units, you have to synchronize it to the system, you have to bring it to the speed, and then you have to connect it to the network. All these steps are to be followed if you run your unit from the scratch. On the other hand, if you have already units in synchronized version, you have already made your units synchronized, then the only thing is left to get the supply from it is this. What I mean is this: if you look at the commit definition, if you have your system already synchronized, you are done up to this step. You have already you have already turned it on, you have already brought it to the speed, you have already synchronized it. Just you have to connect it to the network. This is the last fourth step left to get something out of that generating unit. Okay. On the other hand, if you don't have the unit synchronized, so in that case, what you have to do, you have to turn on that unit, you have to bring it to the speed, you have to synchronize it, and then you have to think about connecting it. So in case of emergency, you can't take that long time. Okay. So this is known as spinning reserve, because when you say your system is synchronized, means what? It is running at a certain frequency, right? And because you are talking about synchronous machine, so your machine is actually rotating at a certain speed, that is synchronous speed. So you have some reserves in terms of electrical power, and your reserve is in terms of rotating equipments. Out of the rotating equipments, you expect the reserve to be supplied, or you expect the reserve to be available to you when needed. So that's why it is known as a spinning reserve. It is not simply reserve, it is spinning reserve. Why we call it specifically spinning reserve? Because there is another term that is coming in the next slide, that is offline reserve. Because just to differentiate between these two, we call specifically this as spinning reserve. I will give example of a spinning reserve with this diagram, so nothing to worry. Okay, so let's say if we talk about a spinning reserve example, the definition says, first let me read out the definition. It says you have the total generation from all the synchronized units. So your units should be synchronized. So that means it should be turned on, it should be brought to the speed, and it should be synchronized with the network. Only thing remaining is it is not connected to the network. So you can say it is floating. Okay, it is floating, the floating status. It is neither supplying power nor consuming power. This is floating status. Minus present load supplied means the current load demand, okay, minus the current load supplied, present load supplied, minus any loss in the network. So if I give it a pictorial view, then a pictorial representation, then we get this. So let's say your current demand is 450 megawatt. You have a transmission network represented by this rectangular block, which gives you 10 megawatt loss. So you have to supply this loss from your generation. So you can say your demand plus loss at this instant is 460 megawatt. Okay, demand plus loss. Now this 460 has to be supplied from your generating units, which are already running or already available. So let's say you have 4 units. Unit number 4 is offline. Okay, you see it is not even connected. So unit 4 is offline, number 1. Unit 2 and 3, these are not only online, but these are actively participating in supplying the demand. Okay, so out of the 300 megawatt capacity, 280 megawatt is taken from G2 and 180 megawatt is taken from G3. Okay, now you see another red colored unit which is shown to be spinning. You see the arrow? The arrow means these are spinning. Okay, these are running. You don't see any arrow here over G4. So it is not even synchronized, not even brought to speed, not even turned on, nothing. It is simply idly sitting there, dead. Okay, dead machine. It's not doing anything. G1 is spinning, it is turned on, it is brought to the speed, it is synchronized. Only thing remaining is it is not connected to the network to supply some power. So effectively, it is not contributing or participating in supplying this load and loss, but it is spinning. Okay, so if in case due to some tripping, generator tripping, let's say generator 2 is tripped, generator 3 is, or generator 3 is tripped, it is instantly ready. Okay, it can provide you maximum 150 megawatt instantly. Just you have to turn this on. So this 150 megawatt, you can say it is one example of spinning reserve, because you have this reserve in terms of it is rotating. So it is at synchronous speed, it is rotating, it is a spinning, it is a reserve. So we call it spinning reserve. So let's say your 180 megawatt is missing, then you can take 150 megawatt and probably you can increase its generation by some extent to meet this. You get my point?
Sir,
Yeah.
the thing is, if generator 1 is rotating all the time, then is it not consuming energy all the throughout the whole time?
Yeah, so you have to make a decision now. Okay, the decision is whether you will keep it running, how much cost does it incur to your economics, or will you risk to have load shedding? Let's say if, for example, this unit is suddenly tripped, okay, in no way you can instantly supply this 460 megawatt. You can maximum supply 300 megawatt, and the remaining has to be shed. I mean, you can't supply. So you are actually losing your customers' satisfaction. So 160 megawatt you can't supply. You get my point? So in so what do you want? You want customer satisfaction. You want to keep your customers under your company, specifically for, I mean, countries like us where you have probably monopoly in power generation scheme. Monopoly, I mean, there are specific companies or associations from where you have to take your power. You don't have any choice. Okay, but in other countries where they have power pool or they have power market, they have multiple power suppliers. They have private power companies, they have public power companies. We only have mostly, we have the combination of private and public, but the rate of power supply is set by the government. Okay, they don't, I mean, the companies, they have contract with the government, and accordingly they will charge you. But if, let's say, the market is open, or the market were open, let's say there is another company sitting there with power, and they don't have this problem, they have sufficient reserve. So if they have any problem in their generation, any of the generators, they can instantly supply you power. So there is no load shedding. And of course, probably they will charge you a little higher because of, you, as you said, you have to run this one, right? You are spending some money here. So of course, your charge will be a little higher per unit electricity. Are you getting my point? So now as a customer, from where will you buy? Will you risk your supply? Will you, I mean, if you don't bother about the reliability of supply, you stay with them. When there is no power, no problem, you are happy. You don't need power, continuity in power. If you need continuity in power, then what you do? You go to them. Let's say if it is an industrial plant, what will you do? So will you just sit idly without the supply when there is a generator trip? And they will take hours to bring it on. They will take hours to bring it on. So what would you do? You have to choose now.
Of course, go for the more reliable one.
You have to choose now. I mean, if you have money, you go for reliability. If you don't have money, you sit idly. There is no problem. You don't need continuity in supply. Okay. So you have load shedding, no problem. You enjoy the moonlight. Go outside. There is a, I mean, big moon outside. You enjoy it. We used to enjoy it in our childhood. Nowadays, you don't face load shedding. very frequently. But in our childhood, whenever there were load sheddings, we were happy. Okay, we used to, come down from our apartments and we used to play with our friends in probably some moonlight scenario. So those things are obsolete now, but we were happy then. But now probably people will not be happy if you have discontinuity in supply. You will no more be happy. Okay, because time is money now. They say like this. Okay, are you clear?
Yes, sir.
So spinning
But
reserve.
sir, one more small point, sir. If since there's no load connected to generator one, the cost for keeping it running would be very small, right? Because there's no force trying to stop it down, right?
No, although there is no load connected, but your 150 megawatt is ready to be available. 150 megawatt is ready to be available. Okay,
Okay.
150 megawatt. You know about super sub in T20 or cricket? Do you follow cricket?
Not that much really.
Okay, there is some reserve bench. I don't know how many of you follow cricket closely, but let me give you one example. There is a concept of super sub. Super sub means what? If you have some concussion issue means, let's say a player gives you a bouncer, okay, it hits your helmet and you are in unconscious, some sort of unpleasant situation, you are not feeling well, so the batsman can be replaced by any other player not playing 11 from the playing 11, let's say the 12th player or 13th player, they can now come and they can continue to bat on instead of that player. Okay, so that player should be made ready whenever needed. He should not be injured, right? He should not be injured. He should be fully fit. He should be mentally fit to serve your team. On the other hand, these players, let's say the 50 megawatt guy, this is you can say those guys who will help you to come into the field during the drinks break. They will carry the drink bottles and the towels and some messages from your what should I say, from your dressing room, from the coach. So this guy is not playing in the playing 11. They will not actively participate. But this guy, whenever called upon, they can immediately participate. So you can call it a super sub, but this one is a reserve. 11th, 12th player, 12th man, or 13th man, and so on. I don't know whether you follow cricket or not, but that is a very, you can say, a very good example. But this has something to do. It is not, I have not simply drawn it without any reason, okay, without any, just for increasing the beauty of the diagram. This player will come into action in the next slide, so wait for that. So of course, as you said, this will incur some money, and of course you can charge it, okay. You can incorporate this issue in your cost calculation, okay. Is it clear now? This 150 megawatt, it is not free of cost. As you said, it can be turned on and turned off very easily. It's not like that. It is still a thermal unit. Remember, G1, G2, G3, all these three are thermal units. Okay, for example, here also we consider it as a thermal unit. So thermal units take hours to get started and take hours to get cooled down. So it's not, although they are not actively participating, but they are ready to participate. They're just one thing is remaining. You have to bring it on, just connect it to the network. This is the only thing remaining. The other preliminary stages have been passed. They have to satisfy all the three. It has to be turned on. It has to be brought to the speed. It has to be synchronized. Everything has to be fulfilled. Only then it can be immediately turned on. Okay. But of course, the cost which it will incur, the increased cost, it has to be taken care of or taken account of during your cost calculation of unit price of electricity. Okay. Okay, so let's move on. Now we look for offline reserves. Okay, now you come for the other players. Now you see this, okay, it should have been probably some other colors, but still it is spinning reserve. Okay, what I am saying here is by red color, I am highlighting only the example here. And in the previous slide, by spinning reserve, I meant this unit, so it was red. In this slide, it is offline reserve, so I'm only making it red. Okay, but still this is spinning reserve. Okay, mind it, this is still spinning reserve. It is still spinning, still it has 150 megawatt, still it is ready to be online. All the steps necessary, preliminary steps are done. It is ready to be connected when needed. Now the difference between the spinning reserve and offline reserve, you can call spinning reserve also as online reserve. Okay, another name for spinning reserve, you can call it online reserve. This one is offline reserve. Okay, offline reserve means it is not even turned on, it is not even synchronized, it is not even brought to the speed, nothing. It is idle, but it is not a thermal unit. Okay, it is a quick start unit. It is a quick start unit with a different cost characteristics. Of course it might incur higher cost. You see diesel generator, you see gas turbine, okay, maybe of not this high capacity, maybe of a small capacity. Okay, pumped hydro storage, hydro units, they need pretty less amount of time for starting compared to the thermal units G1, G2, and G3. So here I am taking this G4 as either a diesel generating unit or a gas turbine unit or any of this. Okay, but it is neither spinning nor turned on. You see the spinning ones are put with an arrow, okay, denoted with some arrow. Here you don't see any arrow, so it is not even spinning, it is offline. So these units can be brought online pretty quickly compared to thermal plants. So these are offline reserve units. Clear difference between this and the previous one?
So this one, for example, the offline reserve will be like IoT generator.
Yeah, IoT generator, these are diesel generating units. They are very quick start, as you know. Okay, probably you have to wait few seconds, very few seconds, a fraction of 1 and 2 seconds or 3 seconds, depending on the start time. So they are very quick start units. You have diesel generating units. That's why you keep them as a standby or offline reserve. Good example. Thank you. Okay. So then you have another constraint, or you can say continuation of the previous constraint associated with reserves. Let's say the reserves, you also would not like to have your reserves concentrated in a certain area or within a certain plant. Let's say this is on the left hand side you have plant 1, and on the right hand side you have plant 2, or this you can say area 1 and area 2. This is your in between, you have the transmission interconnection between them. You have a big network in between, which again, let's say have 10 megawatt loss in it. So you would like to have distributed reserves. Okay, you see some reserves are kept on unit 1 or area 1 in terms of quick start unit. Some reserves are kept in the in your this side, right side, in area 2 in terms of spinning reserve. Okay, these are, I mean, the numbers are not chosen I mean exactly by some mathematical calculation. Some simply I have put some numbers. So 0 megawatt means you have the spinning reserve here, although it is running, it is not supplying. So on the left hand side here you have now 300 megawatt actively participating from G2, and it is supplying, among that 300 it is supplying 280 megawatt. And you have standby 180 megawatt, which is a quick start unit. You have on the right hand side, you have, this is the spinning reserve in terms of 80 megawatt units. Now, right now G4 is participating. Okay, this should be some, okay, I probably made a mistake. This should be something else than G1. Okay, probably I made some copy paste. So just make it G5. Okay, this one, G5. This is another unit. So 80 megawatt spinning reserve. Why you need it distributed? Why you need them to be distributed? Anyone? I mean, what is the problem if I keep all the reserves either in this area or in this area? This is associated with islanding. Okay, islanding. If you have some, let's say some faults on this transmission link, some interconnection, okay, some severe fault, such a way that you have to disconnect this interconnection. Okay, you have to disconnect this interconnection. So through this interconnection, actually what was happening, you were able to transfer power from this zone to this zone, and also from this zone to this zone using that interconnection. But if you have some fault here, let's say, if you have some fault here, okay, some faults here, okay, severe faults, so you have to trip this interconnection. You can't continue operation with this in a safe manner. So in that case, what would happen? You will be left with two areas. Area 1 will be separated from area 2. Okay, so you call this situation islanding. So in islanding case, what you have to make sure that whatever capacity you have and whatever loads you have, you see I have intentionally put loads there, L1 and L2 of different magnitudes or values. So these generation plus reserves should be sufficient to satisfy whatever demand is here, even in the absence of this interconnection. That is in case of islanding. Similarly, whatever generation plus reserve you have, they have to satisfy the demands, whatever demand is here. You get the point? Why the reserves should be spread and not concentrated. On the other hand, if you had only reserves here, let's say in this area, and no reserves here, so what would happen? In case of failure of this interconnection, you could not actually, probably you don't have sufficient generation here, and only solution was load shedding. You get the point? Let's say you don't have 80 megawatt here. You only have a 90 megawatt capacity generator, which is currently supplying 80 megawatt. If the interconnection is absent, you cannot take any power from here, and you cannot, because you don't have this, so you only can satisfy 90 megawatts. So 10 megawatt would have been load shed. Okay, so I think I will stop here because time is up, and we'll take one example on this. We'll continue with this unit commitment issue in the next class, inshallah. Okay, so anything else to discuss? Any question till now? Any other question? So about the quiz, let me repeat, the quiz is finalized to take place on coming Thursday at 8 p.m., right?
Yes, sir.
Okay. So what would you like to have in the quiz? Numerical problems, MCQs, or short questions or conceptual questions? Because the syllabus is ELD and optimization, basic optimization. You have any choice?
So conceptual and short questions and MCQs.
Conceptual and short questions.
And MCQs.
MCQs.
Yes, 3 of them, sir.
No maths.
But
Okay, MCQ could be in terms of maths.
yes, sir.
Okay, let me see how far I can satisfy your demands. Okay, whether it is an equality or inequality. If it is equality, that means you will get whatever you demanded. If it is unequal, then there would be some deviation. Okay. So the class is over. So before you leave, please put your attendance who have already given. Okay, the class is over. Thank you. Assalamu alaikum.